So this video is about a paper from OpenAI that summarizes the ChatGPT architecture, GPT-3 architecture to be precise, and it also introduces something called few-shot learning, which is a technique to specialize models for certain tasks. So let's look into the details of the paper. So starting with the core idea, what you have here first is a collection of data set, right? So maybe you have data from the internet, which contains mathematics data, geography, history, some data around certain different products, customer reviews, etc. So you collect all this data set and you do something called pre-training. So you take this data set and you take a model which has weights which are initialized randomly, and then you perform stochastic gradient descent on this data set, which helps you update the models in the right direction, and finally you get something called a large language model. And the model that you get is more like a generalist, right? So it might perform good on geography in general, mathematics in general, providing recommendations in general. But what about specialized tasks? So let's say you were to have a model which you want to use for arithmetic calculation. So you want to add numbers and you want the model to perform really well on this particular task. So when we talk about specialized tasks, it's not necessary that this general model would perform very well, right? So you need techniques to really specialize this big model to these specialized tasks, and this is what authors talk about, and they propose a methodology to really specialize these models for these particular tasks. And then the question obviously is, once you have performed the specialization, how well does the model perform? So the inspiration for the authors actually comes from human behavior. So if you think of the following problem, right? So you ask a human, what is 1 plus 2 plus 3? So this problem in itself might be easier for a human to solve if you give an example. So let's say you provide an example where 1 plus 2 is equal to 3, and then you ask, okay, what is 1 plus 2 plus 3? And with this example that you've provided, this problem becomes easy for a human being. This observation inspired the authors to also introduce these additional examples to an LLM, to a large language model, and see whether the performance improves. So the idea of providing examples is not newly proposed by the authors, but they explore that this particular setup where you provide more examples, particularly beneficial when the model size grows. So if you have very big models can really exploit these additional examples, and their accuracy is at par with state-of-the-art methods. So this idea behind providing examples is what is referred to as in-context learning, because you're providing assistance to the model to learn from the context itself, right? Note that we are not changing the architecture or the weights of the model in any way, right? So we are just providing examples with our prompt, and this can be done in several ways, right? You're not limited to how many examples you can provide theoretically. So you can provide one example, which was the case that we discussed in the past. You can provide 2 examples, or you can also provide 0 example. And then the question is, how well does the model perform in these different configurations? And what the authors observe is if you have a large enough model, then its performance is quite good on several tasks if you provide enough examples. So that's the key observation, which we will eventually discuss in the later slides. So before we go into the details of in-context learning, there is also another technique which can be used to specialize models, and this one is called fine-tuning. So model fine-tuning is inspired from the pre-training phase. Okay, so what you have during pre-training is you have a bunch of data set, or you randomly initialize the weights, and then you nudge them in the direction to perform well on your training data set. And this is what is pre-training. And if you were to specialize this model, let's say for a particular task of number addition, and you want to do this with fine-tuning, you would proceed as follows. So first you will collect data set corresponding to number addition. So here I've shown some examples, 1 plus 1 equal to 2, etc. So once you've collected this data set, you would perform gradient descent on a loss function. So you would try to change the weights of the model such that the loss function decreases. And the loss function in this case could just be the negative log likelihood, where you're trying to predict the sum of these numbers. So in essence, you're doing something very similar to pre-training, but the weights you start with are an output of the pre-training phase. So you're not starting with randomly initialized weights. And after this process, when you're happy with the number of epochs you've taken, you monitored the loss function on a validation set, etc., you get a final model which is fine-tuned. So authors identify 3 main problems with the fine-tuning approach. firstly, you might not have enough data. To have a reliable fine-tuning approach, you need enough number of data points, and in this case, enough number of tokens. And you simply might not have those many tokens. One example they give is that of grammar correction. Secondly, your model might hyper-specialize, right? So if hyper-specialize to the training data set. So let's say you collected samples and you collected enough of them, but they come from a very narrow distribution. Here I've shown an example. So let's say all your training set and your validation set is coming from 2-digit addition. But what happens post deployment is that you have these out of distribution inputs. So the user is asking for 3-digit addition. And in this case, the model might not perform very well on these test inputs. And finally, authors comment that people don't usually require an excessive amount of training data set for simpler tasks, right? Like think of a task where you're asking for examples of bravery, where you might provide a person with one example of bravery and ask them to create another example. Or you might have a sentence which you ask a human being to classify as being happy or sad. And in this case, again, the human being does not rely on thousands of examples, but rather can solve this problem without having access to any example whatsoever. So in some sense, for certain tasks, fine-tuning a model with a huge amount of data set does not really reconcile with what we see with humans. This statement, although, is not entirely true for hyper-specialized tasks. So if you have a human being who specializes in chemistry and you want this human being to now tackle problems from physics, so you would actually need a huge amount of books and learning material for the human to train on physics, and then the human can start solving some problems on physics. So for hyper specialized tasks, humans do require a lot of training, a lot of data set. But for simpler tasks like arithmetic operations, you might not be in a need of huge number of data points. So this inspired the authors to really look into in-context learning, and this is what is summarized in the next slide. So this is what is few-shot learning or in-context learning, whichever way you want to call it. The text that you would plug into the model would contain of 3 parts. First would be the task description. So here we have a translation task, and the task description is, can you translate English to French? And this is stated in the beginning of the prompt. Then you have these 3 examples, right? And these 3 examples are in some sense guiding the model or helping the model to accomplish the final task. The final task is translating cheese into French. Here we have 3 examples as I said before, and then the final task is given in the end. So this is what is referred to as K-short learning. Here K is the number of examples that you provided the model. So for this particular case, K will be equal to 3. And authors try to distinguish cases where you only provide one example and where you don't provide any examples. So this is the case for one-shot learning. So in case of one-shot learning, K is equal to 1. So you only provide one example. And this is actually quite a common way to communicate tasks to humans. And that's why they make this distinction. In practice, we don't usually see humans being provided with more than one example, and that's why authors make this distinction of one-shot learning and zero-shot learning. So in case of zero-shot learning, you don't have any examples whatsoever. One example of zero-shot learning is translation tasks. So if assuming a human being knows how to speak a certain language, they can just directly perform translation without having the need of examples. So this is what is called zero-shot learning. And authors suggest that eventually we would like models to perform in a one-shot or a zero-shot setup, but that's difficult, and this is what we would strive for in the future. So this is something that is more comparable to human level performance. But for now, we would stick to a K-shot setting, where K is much larger than 1. And the value of K, as you can see here from the prompt itself, if the value of K increases, then your prompt length increases and the number of tokens in your prompt increase. So K, you're limited by the context length of your model in choosing the value of K. Usually in practice, authors observed very good results with K in the range of 10 to 100, which is much larger than one-shot learning and zero-shot learning. But for certain examples, and we will come to that later on, For certain examples, the model performs very well, even in one-shot setup and zero-shot setup. So in certain tasks, it is possible to have a human level framework where you're not giving a lot of examples and still the task has acceptable accuracy. So as we will discuss in the later slides, authors they look into different sizes of models, and these are summarized in this particular table. So as you go down the table, the complexity of the model increases, and finally we have the GPT-3 model, which has 175 billion parameters, as is noted in the first column. And you will see that you really need bigger models to exploit few short learning. With smaller models, you will not be able to get accuracy that beats state-of-the-art models when it comes to providing additional examples or doing in-context learning. So just a quick discussion on what these different columns mean. I have discussed all these parameters in one of my previous videos. So first one is the number of layers. This corresponds to the number of transformer blocks you have. Then D model is the internal dimension of the model, and you can see this increases as the complexity of the model increases. Then you have the number of heads, which is the case with multi-headed attention. So you can have multiple heads working in parallel to collect different types of information. And then D head is just the dimension of one particular head, and this is obtained by dividing D model by the number of heads you have. Batch size is just the size of the number of sequences you will consider while performing one gradient update. And finally, we have the hyperparameter, which goes into the optimization routine, and the hyperparameter decreases as the size of the model increases. So here you can see that compared to the smallest model, GPT-3 is 100 times bigger, and the learning rate decreases by a factor of 10. So let's talk about the training data set, which the OpenAI team used to pre-train the GPT-3 model. And the most common data set here, which is used by many companies, is the common crawl data set. And this results from a web crawler that goes to different websites, collects all the text and puts it together. And the data set is huge, right? It has more than 1 trillion words. This leads to an incredibly huge corpus of training data set that you can train on. But obviously, the data set is noisy because you're collecting all the information from the internet. You need to undertake certain steps that improve the quality of this data set. So the team undertakes 3 different steps. The first is filtering bad documents using a reference to clean documents, and I will discuss this in detail in the next slide. This step is a little bit more involved. The next step is document deduplication. The training dataset can contain several documents which have multiple duplications or overlap, and when you have these overlaps, the model will try to fit better to these duplicated documents, and this is something you don't want. The team deletes or removes these duplicated documents, and the way this is done is by first embedding all the documents in an embedding space, and once you've embedded these, you can measure the similarity between different embeddings, and if the similarity is higher than a particular threshold, you can conclude that there is an overlap, and you can remove certain documents from the neighborhood of these similar embeddings. So after you've removed these duplicate documents, you're left with 90% of the data set. So you remove 10% of the data set because of duplication. And finally, you have in some sense a broadening of the training distribution with higher quality data. The authors include wiki web pages or certain ebooks and certain amount of web text data which is considered to be of higher quality. So coming back to filtering bad documents and how this is developed. So what we have is a following framework, right? So you would like to, given a document, you would like to know whether it's good or bad. So it's a classification task. And to build a classification model, you need 2 types of examples. You need positive examples where you have high quality data. So this high quality data is coming from Wikipedia, books, web text, etc. And then you need negative examples, and in this case negative examples is the entire web crawl dataset. So the authors are assuming that the common crawl dataset is overall it's noisy and it can be considered as a negative example. So once you have these examples, you can embed them, and once you have the embedding vectors, you can train a logistic regression classifier, and this is what the authors also do. And once you have this classifier, you can you can make a prediction on the probability of a document being good given certain document. So this is a classic classification setting where you're given a document and the output is what is the probability that the document is good or not. Now, using this probability, you can construct something called a document score, and this information is actually missing in the publication, so I'll skip it. But let's assume that using this probability, you can construct a certain document score. Now, the question is, once you have a document score, how would you select good documents, right? So what authors do is the following. So they first compute document scores for all the positive examples, and then they fit a Pareto distribution on it. So what this distribution is telling me is the distribution of document scores for good text. And now if I sample one number from this Pareto distribution, this is a sample for a good document score. So all I need to do is to check whether my document score is greater than the sample I've chosen. Okay, and this is what this equation is doing. So you have a document score for a certain document, and then you've chosen a certain sample. So you randomly sample Pareto distribution that was fit on all the good document scores, and then you check, okay, whether this inequality is satisfied. So this Pareto distribution is a heavy tail distribution, and this is how it roughly looks like. This is a Pareto type 1 distribution that starts at value 1, but here authors have used Pareto type 2 distribution, which is nothing but a shifted version of this particular distribution, and the shift is such that the values start at 0. Okay, so it's a thick tail distribution. So what would happen here is, usually you'll have a high number in this case, so you'll select documents which have a good document score, but in some cases you will also have a low value sampled from the Pareto distribution. You'll also have a low value sampled from here, and in that case a noisy document might be selected. And authors argue and that this is actually nice, because you're exposing the model to at least some out of distribution information. Now, why the Pareto distribution was chosen is really not discussed in the publication, but I think you can in principle also use other type of distributions to really do this particular sampling. So this is how the filtering of documents work, and I think the same process could be used for other type of applications where you have noisy data and you want to get rid of many of the noisy documents. Obviously, you can't do this manually because it would require too much effort. So next comes a few results on several different data sets. So first one is LAMBADA, and this is a very interesting data set, I believe. So you have something called a last word prediction problem. So you give the model a big paragraph, and the model is supposed to predict the last word, right? And what you're measuring here is how well the model keeps track of long context length, and how does it keep a track of references, whether it can understand coherence, whether it can track characters along long sentences. So that's what we're trying to measure. It's only a last word prediction problem, so we measure whether the word is correct or not. So the metric we use here is accuracy. So this is how the results look like. So first observation is that on the x-axis you have parameters. So different degrees of models are on the x-axis. Here we have the very last data entry. This corresponds to the GPT-3 model, right? And here we have the GPT small model. On the y-axis we have the metric, which in this case is accuracy. We have the human level performance, which is above 90%. Then we have the SOTA model, which does not use any examples whatsoever. So this is the zero-shot learning paradigm, where SOTA model is not using any examples, and it has been fine-tuned on this particular task. So firstly, if the models are on the smaller side, then you don't gain much by few-shot learning, right? And this is what we see here. So you don't have much gain on smaller models. So although your context length has increased, the number of input tokens have increased, so your computation are now taking longer, you don't gain a lot in terms of accuracy. So zero shot, which is the blue line, is actually outperforming in most of the cases. It's outperforming the few shot case, where k is equal to 15, and the one shot case for smaller models. But the scenario changes entirely if you have bigger models. So you can see that for bigger models, especially the GPT-3 models, it actually outperforms the state-of-the-art model by quite a substantial amount, right? And all the three approaches outperform the SOTA model. But something strange is happening here, right? So the one-shot model is actually performing inferior to the zero-shot model, and this is also surprising to the authors, and they don't really provide much of an explanation of why this particular phenomenon is taking place. So what could be the reason behind getting such spectacular performance from a few examples and beating the SOTA model just with k is equal to 15 examples? So one explanation which authors provide is that this task in itself, this last word prediction task, this is quite difficult for a large language model. So this is easy for humans, but for large language models, they don't really know whether this is a last word prediction task or whether this is a next word prediction task. Okay, so this distinction is not there. If you just plug in this example into an LLM and ask for the completion, it might get confused and try to have the next word rather than the last word, which might not be the same. So last word might not be the same as the next word. So but when you augment your prompt with some examples, then it really makes it clear to the model that this is a last word prediction problem. And with this additional information, it can really outperform even the state-of-the-art techniques. So let's look at the other example where we have something called HellaSwag. So this is a story completion task. You're given a certain story and you're given then multiple choices. Out of these multiple choices, you're supposed to select the correct completion for the story. So all the choices are grammatically, semantically correct, but only one of the choices makes sense in relation to the story. So again, you're trying to understand whether model can hold information on long context, whether it can understand references, whether it can comprehend the different intricacies in the text, and the metric here is again accuracy, because the model either chooses the correct answer or it doesn't. Now the SOTA model here performs actually quite well. It gives you an accuracy of around 85%, and this is a big multitask model which has been fine-tuned to this particular task. And then comes our GPT-3 performance with the few short setting, and this is quite impressive, but still lower than the state-of-the-art performance. And finally, you have one shot and the fine-tuned model tuned particularly for this particular task. So both few shot and one shot beat this fine-tuned model and perform very well, even when compared to the SOTA model. And remember that we are not performing any fine-tuning whatsoever when we are performing few shot and one shot operation. So next we have a closed book question answering session. And this is also very interesting. So closed book basically means that the model does not have access to all the information out there in documents or on the internet, etc. In case of open book, the model does have access to this additional information, and this additional information can then be used by the model to provide better answers. But in case of a closed book setting, we don't have this configuration. So it has been observed that larger models are pretty good in a closed book configuration, and that's why authors use this particular test. So the results I've shown on the right, these correspond to a dataset called TriviaQA. TriviaQA dataset is a collection of certain trivial questions, and one example could be who wrote 1984. Again, the performance is measured with the help of accuracy. So either the model gets the answer right or it doesn't. So in this case, the model performs exceptionally well as compared to the SOTA model. In the few short setting, we are already beating SOTA by 7 percentage points in terms of accuracy, which is remarkable given that we are not nudging the weights whatsoever. The one shot setting is actually 4% better than SOTA, and that too with open book, right? So the SOTA model, which has access to all the additional information to solve this particular question, is actually performing worse than our one shot setting. And what is surprising here is even with zero shot, right? Even with zero shot, you can beat a fine-tuned model by 14 percentage points. And I think the reason for this is that the GPT-3 model is a huge model. So it's able to store a lot of information in its weights. And this information allows us to really answer these trivia questions without providing any examples whatsoever. Another example that's coming from arithmetics. And we're looking at very simple operations like 2-number addition with 2-digit, 3-digit addition, or 3-number addition, etc. And the metric here will be the same as previous examples, right? Either the model gets the number right or it gets it wrong. So accuracy is the one that's used, and the results are shown here. And let's try to understand the different components of this plot. On the x-axis, again we have the number of parameters as before. On the y-axis we have accuracy, and now we have different curves for different types of number of digits we are adding. So first we have the blue and the orange curve for 2 digits. Then we have curves for 3-digit and so on. And authors have done computations till 5-digit addition, subtraction computations. So there are mainly two takeaways from this plot. The first one is that again, right, similar to the previous cases, if you don't have enough parameters in the model, then the performance does not benefit from these few short type of from this few short type of an approach. Although in this case you do see that the results are not as noisy as for the previous cases, but still the accuracy bump that you get compared to the bigger models is not substantial. Now, if you move to the right of the plot, and when the models are big, they benefit substantially from this few short k-short learning approach. Another thing that's very interesting, but also probably expected, is that as you increase the number of digits, right, the accuracy goes down. So for 2-digit operations, which are shown here in blue and orange, the accuracy is close to 100%. Then you have a drop in accuracy, which is dropped from 100 to 80. But after 3 digits, the drop is very substantial. So you suddenly have a cliff along which the performance drops. So from 80% you drop straight away to around 25% for a 4-digit digit manipulation. So in addition to these test cases that I've discussed, there are also plenty of other examples showed in the paper, and I would highly recommend you to go through the paper if you're interested in learning more about how to evaluate these models, what type of data sets are available, and what different types of testing could be done to really understand how well the model performs. So before we end this discussion, I want to briefly review one of the important sections which the paper contains, and this is about test set contamination. So what happens is, because you're training the model on a very big data set, it's possible that some test points in the test set overlap substantially with some of the test points in the training set. And this is what I've shown here. So here you have this blue dot, which is overlapping with another blue dot in the test set. And if you do this, then the performance of the model on the test set is not representative anymore of its actual performance, because you have minimized the loss function on the training set. This overlap would result in a more optimistic result on the test set. Now, this is more of a problem if there is huge amount of overfitting, and authors argue that their training regime hasn't really reached the overfitting regime. So if you look at the different training curves, which are shown here on the right, each of these different pairs of training curves correspond to different model sizes. And you can see that the validation loss, which corresponds to the solid line, and the training loss, which corresponds to the dashed line, they're both moving together. We don't see a divergence between the validation loss and the training loss. So this shows that we haven't really reached the overfitting regime yet. So if the model hasn't really overfitted on the training set, it is likely that the estimate you're getting on the test set might not be that bad, even with the overlap. So to really validate this and to understand the effect of this contamination, authors proceed as follows. So first, what they do is they try to basically divide the test set into a contaminated set and a clean set to identify the dirty examples or the examples which overlap with the training set. They take the following approach, and I think the approach is very conservative. So you'll get a big fraction of test points which are actually overlapping with the training set. So this is how the approach looks like. You take the test points, and then you construct 13 grams of sequences from them. So this corresponds to splitting the text into all possible 13 length sequences. Okay, and so once you've done that, you can just check if any of these sequences overlap, and even if one of the sequence overlaps with the training point, you remove that test point. And when you do this approach, you can split your entire test set into two parts. One is basically the dirty test data, which is having overlap as per this criteria, and then you have the clean test data, which does not have this overlap. So now we want to understand what is the effect of this overlap that you had in your test set. And to understand this, we will compare the metric we calculate on the entire test set, including the overlapping data, and then we will compare that metric to the one computed on the clean test data. Okay, so when you make this comparison, you'll be able to see what's the influence of the overlapping test points. So this is how the results look like. And let's, because there is a lot going on in this plot, so let me explain the different components. On the x-axis, you have the percentage of clean data present in the data set. So each of these blue dots correspond to the different test sets which were considered in the paper. On the y-axis, we have the difference in performance between the entire test set and the clean test set. Okay, so let's say you compute the accuracy on the entire test set, and then you compute the accuracy on the clean test set. You take the difference, you take the percentage difference, and that's what gives you the y-axis. Now, if the blue dot is above a value of 0, that means that the evaluation on the clean set was better. And if the blue dot is below 0, then it means that the evaluation on all the test set, or the evaluation on the entire test set, was actually better than evaluating things on the clean data set. Another thing that's important is the further away you are from this horizontal line of 0, the worse is the effect of this dirty test set. So what we see here is, under this conservative approach of detecting overlap between test samples and training samples, you have a high degree of contamination, definitely. But despite the contamination, most of these blue dots lie close to 0. That means the difference in performance between the entire test set and the clean set is not substantial. And yeah, so this in some sense validates the hypotheses of the authors that since they haven't reached the overfitting regime, having some overlap between the test set and the training set won't really hinder the performance evaluation. Now, only for very few data sets do we see a substantial deviation between the performance. So here, where the percentage of clean data is super tiny, almost close to 0, there we see that the gap in performance is huge, and this could also result from just statistical noise. At this point, the amount of clean data is so little that I don't think you can get a substantial, a statistically significant measure of the difference in performance. So other than these outliers, right, the performance is in general very similar on both the entire test set and the clean data sets. And I think this type of study is extremely important when you're developing models, right? So you want to understand whether there is any overlap between the test set and the training set, because otherwise you won't have a reasonable estimate of the model's performance. And with this, we come to the end of the video. Make sure to subscribe the channel if you want to be updated with latest machine learning literature. See you in the next videos.